All right, folks, today we're going to talk about translations on the graph. So we talked about scale change first. Traditionally, when we first started talking about transformations of functions, we actually looked at a translation first because, in general, they usually are easier to see on a graph. Our purple note card had something where there was an A outside grouping symbols, then BX minus H and plus K on the outside. And then the H and the K were telling us about translations. We kind of skipped around for trig functions because when we talk about translations, if we're going up and down on a graph, that's no problem. But when we go left and right, if we think about the sine graph or the cosine or the tangent, we have those pi values or the angles in radians, which creates fractions and makes the left and right translations just a little bit more difficult. So first we're going to give some descriptions for our H and K from this formula. H they give a special name, phase shift, and the reason it has a special name is because if we talk about a translated sine graph, so something that doesn't start right where it's supposed to, we can see that there's a shift of whatever that distance may be. But because the sine function and cosine and tangent are all circular and they start to repeat themselves, we could call it just this translation or all the way over there. Okay, so the phase shift by definition is the least or the smallest distance from the original. Vertical shift, what you see is what you get in terms of the equation. If you see a positive, it's negative, whereas here, because the original formula says opposite of H, we'll always have to shift our thinking in terms of the left and right. So let's go ahead and look at the first example. They give us the parent function sine, and there's a plus 2 pi over 3. Just like with our original graphs, because of this negative in our equation on the purple note card, this goes the opposite direction that you think. Okay, we know it's left and right because it's grouped with x, and x on a graph goes left and right, but opposite, this is going to go to the left. So our phase shift is the h value, or the negative 2 pi over 3. Okay, now what we're going to do is take a look at what's different. Instead of an equation here, they're giving us the rule. Let's mark it as that. Usually when we see the rule, there's a capital letter in front of the first ordered pair to talk about a translation or a scale change, but the formula tells us what's happening anyway. This says take all the y values and add 2 to them. Well, if we think about what that does on a graph, if you take all the y values, that's the up and down stuff, and add 2, it goes up 2. So we can see it written as the rule instead. What's really important for the rule, I don't care if it's the x or the y value, what you see is what you get. If you add, you go right or up. If you subtract, you're going to go left or down. We're going to use this to sketch. So what we want to kind of bring back is the amplitude and the period for the original sine graph. If we talk about a translation, neither of these things will change. So the amplitude of the regular graph is 1. And the period of the regular sine graph is 2 pi. Do not change under a translation. Okay, so let's go ahead and just emphasize, do not change unless there's a scale change. And we talked about that being the A or B value from last time. Okay. What does change, though, is if I'm shifting a graph up, that means the maximum point and the minimum point change. So what I want you to do is make a little bit of space for max and min, and that's going to help us graph this. Okay, so in general, we're thinking about our old maximum and old minimum. Because our amplitude is 1, it is just positive 1 and negative 1. And then we get to just plug in our rule. It says add 2, and we'll add 2 to both of those. So maximum is a positive 3, and minimum is a positive 1. So you'll notice that our scale was left blank on here. That's so we could choose numbers that are appropriate for these values. Looks like counting by ones will be good for us. And here's what I want you to do, at least for these first couple, is we're just going to dash on lines to give us some guidance here. So we decided our highest point was going to be 3, so I'll put a little dash line there. Lowest point is 1, dash line there as well. And that tells us we'll cycle in between those values. So we just have to think about the original sine graph. If it helps for you to make a little baby sketch like we practiced last time, let's do it. Okay, so sine starts at 0 and then cycles. So we're going to imitate this, but instead of being cycling between -1 and +1, we're cycling between 1 and 3. But what we're going to focus on is the beginning. We used to think about either the beginning being at 0 or at 1, and I want to be more general than that even. Instead of thinking about 0 or 1, I'm going to ask you, does sine start in the middle of the graph or at the top of the graph? So sine starts in the middle, whereas cosine starts at the top, its maximum. So what we're going to do is use these lines, since sine starts in the middle, and just plot a point in the middle. Okay, then we just follow the same pattern we normally do. There wasn't any translation left or right, so we're staying right on our regular values, pi/2, pi, 3 pi/2, and so on. We go up first, then back to the middle, down to the minimum, and back up to 0, just following the pattern of sine. Then you can do that same thing over on the left, and when you're finished, connect your points. There's no rules for restrictions here, so arrows are fine on these ones. Just make sure, remember when you're connecting these, to try to curve for your max and your minimum, so it doesn't look like a jagged line. And that's it for the translation. The next one we're going to look at is just a true or false, and it kind of deals with what we just graphed. It says the graph of any circular function, or repeating, and its image under a translation are congruent. If we compare this graph that we did with the translated 2 with the original graph, other than we graphed the first one just really tiny, they are the same size and same shape. This one has just moved up. With that in mind, congruent means same size and same shape, so this is true. The only thing that's going to not be congruent is a scale change. Translations, reflections, rotations, they are congruent. All right, what we're going to have to think a little bit harder for is a translation left and right, which is happening on number 4. I know that, again, because anytime something's with x, which goes left and right on a graph, we have some sort of translation that same direction. So remember, phase shift tells the direction. If we see a plus pi/3, it's going to be a negative pi/3, or to the left. All right, with this, again, just for good practice, we're going to start with our maximum and our minimum. And because we didn't have a translation up or down on the end here, it's going to be at 1 and -1. So I'll stretch this one out just a little bit, put my 1 up there and my -1 down there, and dash on my lines. Okay, what's going to be different here is we still talk about the starting point, but because we'll have a translation, we'll have to move it over one direction or the other. Okay, so little baby graph again to give us some guidance of what's happening. Cosine starts at the maximum. And this graph starts at the top, so we're going to take this top point, but before we plot it, we decided we had to move left pi/3. Okay, I like to think about decimals here to help with graphing. So pi/3 is like 1/3. We'll just look at that value since all of these are in terms of pi anyway. So that's 0.3 repeating. And if we think about what's labeled on our scale, this is 0, just regular 0. 1/2 is -0.5, and then -1, -1.5, and then -2. We just have to see where that would fall. Once we have that one, we'll just use the pattern to graph the rest. So this 0.3 falls closer to 0.5 than it does to 0. So at the maximum, we're just shifting over, and our new point is there. Specifically, if we wanted to write the ordered pair, it's that -pi/3 at the maximum of 1. All right, but we're just going to use our pattern to graph all of these. Okay, so the whole idea is we're shifting over this amount with our whole entire graph. So our next point is usually in the middle, and it's usually at pi/2, but we're just going to shift over that same amount that we did there. The next value is normally at pi, okay, and that's the minimum. we're just going to hover over and shift it to the left, that pi over 3. So if you'll notice, at every one of our marks here, our point is just a little bit to the right of it. So here at pi over 2, we're going just a little bit to the right of it. At 3 pi over 2, we have to be up, but we're just going a little bit to the right of it, and just following that pattern along throughout our graph. Okay, so we'll end a little bit past 2 pi, and then continue that towards the left as well. Okay, so I've already got my one next to pi over 2. Next to pi, we're going to put a mark. Next to 3 pi over 2, down below, and so on. And then we're just going to connect our curve. It just says complete 2 cycles. So exactly 2 cycles would look weird. I'm okay with you just putting arrows here. All right, we're going to go back to the rule. Mark this. We talked about it a little bit at the beginning, but this is the rule because we see this ordered pair. And remember, rule gives direction. So what you see is what you get no matter what side you're looking at. Okay? Amplitude and period do not get affected by translation, so still 1, and period, we'd have to know whether it's sine, cosine, or tangent. Looks like we're talking about sine in part B, so it is 2 pi. Remember, period of tangent is different. It's regular pi. Then it just asks for the phase shift. So remember, phase shift is the weird one. It's the horizontal value, the h. And because this says go right 3 pi over 2, the phase shift really is 3 pi over 2. Or 4, sorry. But we don't switch the sign because this is the rule. We only switch the sign, okay, when we're talking about the equation, which is what we're going to do now. Okay, so the equation, starting with y equals, okay, first thing it's sine, but inside, instead of writing that plus 3 pi over 4, we're going to write minus. So put your x first, minus 3 pi over 4. We just switch what we saw from the rule to the equation. The k value doesn't change. This says y minus 3 because it's going down. We say down the same way, whether it's the rule or the equation, just with that negative value. Next thing we're going to do is write the equation from the graph. And it doesn't give us whether these are sine or cosine, which means you can choose whatever you want. Sometimes on your homework, I'll specifically ask for one or the other, but you'll just have to pay attention to what it wants. Either way, what we're going to do is always mark the point that we're going to start with to talk about the translation. Here's what I mean. With these both being waves, we could think of them as sine graphs. And usually sine graphs are starting at the middle and then going up afterwards. Or we could think of them as cosine graphs, and cosine graphs start at the maximum and go down. So what you're going to check out is just the x-axis or the y-axis, because that's what we're looking at first anyway, and just figure out what's closer. Is the 0 closer, or is the maximum closer to where we're starting? So looks like for this one, the 0 right here is closer than that maximum is. Okay? And that is the point that we have to figure out what it is so we know how much it's changed from this original graph. All right. Well, to do that, we're just going to kind of use the patterns of our graph here. And with that, we'll know it has to go right when we write our equation. Okay, so we'll think about that. All right, let's chat just for a minute. With a sine graph, with a cosine graph, no matter what, when we talk about a period, we mean the distance it takes to complete a cycle. So for us, here we see our cycle, and how it normally looks is that's 2 pi. All right. Well, they gave us 2 points here, but neither of them were necessarily the point that we needed. They gave them to help us figure out the point that we need. There's 2 ways to think about this. Okay, one of them is recognizing that the period, or 1 full lap, happens between those 2 values. And for this graph, even though it's shifted over, it's still a distance of 2 pi. negative 2/3, positive 4/3 add up to 6/3, which is still the number 2. Okay, with that, we know that the middle is exactly pi away, and this dot is directly in the middle of those two values. So I know that this distance is pi. If I wanted to find this ordered pair, I can take negative 2/3 pi and add pi. Okay? If you're not comfortable with fractions, you just take this negative 2/3 and you take this 1 and you type it in your calculator, negative 2/3 plus 1. Okay, but here this is negative 2/3 plus 3/3, it's a positive 1/3. And then we can label that on our graph. Okay, that's option 1. Option 2 uses the same idea, but just averages. I'm going to erase all these markings here. It still uses the idea of the middle. If this point is directly in the middle of those two, you can literally average them to find the value. Average means add them up and divide by 2. So you can take your negative 2/3 pi plus 4/3 pi and find the average. So this would be 2/3 pi. And then it says divided by 2 or times by 1/2, and you still get 1/3. Okay, usually I like using this better only because we don't have to worry about dividing by fractions where we do with the average method. Okay, now that we know the point, we can answer the question, and that's just writing the equation. So we decided that it starting in the middle was closer, which means sine was the better equation. And this was to the right. If we want to write to the right, we have to say minus the number. And that's it. Okay, on number 7, hopefully you noticed that this is not cycling around where it's normally supposed to. So what happened is we had a translation up. Okay, if you mark where the maximum is and where the minimum is, that'll tell you what happened. Okay, we normally start around the center, and I'll go ahead and mark it here. See how the center on this graph is right in between your maximums and your minimums? This tells you there's no k value, because that's what it's supposed to do. But our center for this graph is way up here, and that tells you the k value directly. So our k is 2. And we can start out on our equation automatically because k, we don't have to worry about switching the sign. What you see is what you get. So we know we're going to have to end in plus 2. But the next thing we have to decide is with your y-axis, what equation is better. So with our y-axis, it actually automatically starts in the middle. And if it automatically starts in the middle, we're just going to use regular sign without having to worry about a translation at all. So y equals just regular sign x. If you want to put parentheses around that x, you can, but if you don't see them, that plus 2 has to be outside. All right, tangent looks uglier, but it actually is easier to do most of the time because of the asymptotes. Okay, so what I want to do is take a minute to refresh our memory on what regular tangent looks like. Okay, so we start at 0, and then every pi over 2 something happens. So the first thing is the asymptote. Then at pi, we're back to a 0. Then there's an asymptote again, and it just repeats that process on the other side as well. So we've got curving through the middle. This middle point that I've marked is the x-intercept or 0, but it also has another name that's special. It's called an inflection point because this part of my graph is concave down. Looks like it's pointing a cup down. And then this side is concave up. So that inflection point is usually along the x-axis. If it's not, we have a translation up or down. Okay? Then, similarly, it's supposed to start at 0, 0. And if it's not, we have a translation left to right. Okay, so if anything is not 0 on that ordered pair, we've got a problem. Now, sometimes they will, instead of marking the point, they'll mark the asymptotes. Just remember on your unit circle, tangent is undefined at pi over 2, 3 pi over 2. All of those half pi values. If they're not, there's a translation left or right. Okay, so let's go to work on looking at this first one. We're looking at the graph and looking at 0, 0, the point they marked, and it's not at 0, 0 anymore. It's definitely the inflection point, so it's definitely supposed to be in the center, but you'll notice it moved over. Okay, we need to know how much over, and they labeled it for us, which means we don't have to do any math like we did on the previous example when we had to figure out this point that was missing. With that in mind, we just have to write how we say left in the equation. So y equals tangent. If we're talking left and right, it has to go inside the parentheses, and it's always opposite inside. So this said negative pi over 4, we have to say positive pi over 4. And that's it. There was no up or down because that y value was still at 0. Okay? If we're looking at this one over here, okay, we do have some things happen. In fact, we have two different things happen. The x value is not in the right spot, and the y value is not in the same spot. Okay, both of those things are problems. What I want you to do is pause the video and see if you can figure out where that is supposed to be. All right, so this point was at 0, 0. And it's moved to the right, pi over 2. Sorry, that's not supposed to be negative there because it is on the positive side. And it also went up 1. So putting it together, y equals tangent. Inside is left and right. We went to the right, so we actually write minus pi over 2. Okay? Then outside, we want to go up, so plus 1 on the outside, and we are done. Okay, so tangent looks bad, but actually, usually they label the point for us, and that makes our life a lot easier. All right, 10 through 12, just using sine and cosine asks you to match the equation to the graph. I want you to pause the video and see if you can do that, and then you can press play to check your answers. All right, here. C, B, and D should have been your answers. Here's what I would start with. This means down, and the only graphs that went down are A and D. But because there was no left and right, sine has to start in the middle. So if you look at your maximum and your minimum along the y-axis, this one actually starts in the middle, where this one starts at the top. This would be a cosine graph. Okay? So once you've done D, both of those are gone, because these equations don't have vertical translations, and you just have to decide between B and C. Okay, you'll see this hits at pi over 2, so that's that shift. This one doesn't hit at those nice values, so it has to be the pi over 3, but you can also look at direction. Okay, normally sine starts at 0, 0, or in the middle where it goes up afterwards. This one went to the left, whereas that one went to the right, meaning we have to do the positive with the left and the negative with the right to kind of match those up. We're going to do a couple more graphs to make sure that we can do both a translation left and right and a translation up and down at the same time. This is the first graph we've seen with both. Okay, we'll do the first one together, and I'll have you do the second one on your own. So first thing, let's make a little baby sketch to know what the original parent function is supposed to look like, and then we can translate it based on the numbers. So cosine starts at its maximum and goes down. And then let's just chat about max and mins while we're at it. So I'm going to do it down here. I've got a little bit of room. So our old maximum for cosine is 1 because there's no amplitude change, and old minimum is -1. Again, no amplitude change. And then of these two things, what's going to affect up and down is the +1. That's our k value. So you'll just add k to both of these. You might make yourself a note of that. So this would be +1 here and +1 there. So +2 and 0 are going to be the numbers we're cycling around. Let's go ahead and fill out our scale so that we can dash those lines on there. Okay, so you can count by ones or you can count by halves and spread it out here, which is what I'll do. And we're going to cycle from the top being 2 and the x-axis. Then we just have to figure out what this means so we can graph each of these points. When you see a minus pi, this means to the right pi. So every time we plot a point, we're going to make sure that we move it over pi. So cosine starts at the max, and before I plot that, I'm going to move it to the right pi. So I'm going over and plotting my point there. All right. If you want to go point by point, you can. Here's what I mean by that. The next ordered pair would be here, pi over 2, okay? But it's been shifted up 1 and right pi. Okay, but what I like better than that is once you find your first point, like we did here, all you have to do is follow the pattern from your graph. And that's why these guiding marks will help you. Because we haven't had a scale change, something important happens every pi over 2, and we just follow the pattern. We have to go all the way down to the minimum and all the way up. So we've got the middle, then we're going down again, and it would start going back up again, but we're out of room. On this side, to the left of the starting point, we go down, so in the middle at pi over 2, at the bottom for 0. And then just keep going all the way through. Once you're at the minimum, you have to go back up, then hit the maximum, back in the middle, and the minimum. And we can go ahead and complete our graph. Now this does say go from negative 2 pi to 2 pi. That means endpoints rather than arrows. And there's our graph. Last thing it asks us to do is, once we've graphed it, find all points where the function attains its maximum. So here, this is the ordered pair negative pi 2. And this other one going to the right is pi, and then same number 2. All right, I told you I was going to let you do 14 on your own. Okay, so draw yourself a practice sketch and then figure out where your max and minimum are going to be after the translation. Pause the video and get that done. All right, so everything's shifting up 2 here instead of 1. So we're going to be at 3 and 1 instead. Got to count by ones on this one. And with this one, sine starts in the middle. So it would start here, but again, we have to change this value as well. This is going to the left pi. So my first point would be here, and then the sine graph, if you look at your practice, goes up from there. So using that pattern, up, middle, down, middle, up, middle, and so on. Other side, we're going the reverse. We're going down first, back to the middle, and we can sketch our graph. These ones are a little bit easier to graph because they fell on nice values for translations. Anytime you hit a pi or a pi over 2 and your scale is labeled this way, they're not so bad once you get the starting point. It's problems like when we saw the very first graph here, where we had to shift it over a strange amount by graphing it, this one, where they don't hit those nice points where you have to just think a little bit harder while you graph them. All right, on this one it just asks us to label the x and the y-intercepts. There are no x-intercepts, there's only a y-intercept. It does say label it, so put it on the graph, but I'll throw it on the line as well. Okay, last thing we're going to do here is talk about tangent. It is the most difficult to graph, whereas getting the equation when you have the graph isn't so bad. Graphing it yourself takes a little bit of work. Okay, again, we're going to decide about this and what it says. We see a minus pi over 6. That means we're going to the right pi over 6, but we don't have to worry about going up and down at all. In the case of tangent, we don't have to worry about a maximum or a minimum because there aren't any. It goes on forever in both directions. Instead, what we're going to focus on that makes it a little bit more challenging is the asymptotes and how often they show up. Okay, so normally, okay, we have to think about where the asymptotes are. I'll go ahead and sketch it to the side. Do this with me, please. Just like we had been, we're going to do a little practice sketch before we do the original, the new one. So starting at 0, then dashing it, then 0, then dashing it. Do that on the other side. Dash line, 0, dash line, and then we can fill in our little swoops. Instead of plotting the points, we're actually going to do the asymptotes, and then we'll just put the points in the middle. It'll make our life just a little bit easier. And really, if we focus on one asymptote, we can find all of the others pretty quickly. Here's what I mean. If you know where the first value of tangent is, all we have to do is take this rule and apply it, and then every other asymptote after that is the same distance apart. Remember, the period of tangent is pi. So hopefully you remember that the first asymptote is at pi over 2. If not, remember, think unit circle. At pi over 2, we've got 0, 1, and 1 divided by 0 is undefined. Okay, that's where it's coming from. But what we're going to do is figure out where it goes if we want to move it to the right, pi over 6. So this is where we're going to show some work, kind of like we did with that one graph where we had a weird number. So we're starting with pi over 2, and we're just adding, because we wanted to go to the right, the shift that was pi over 6. Again, if you're bad with fractions, you're just typing 1/2 plus 1/6 in your calculator. Okay? But 1/2 is 3/6, plus 1/6 is 4/6, so we're ending up at 2/3 pi. And we're going to graph that. So again, think decimals. This is 0.5, this is 1, 0.6, a little bit closer to that 0.5. And we'll label it. X equals 2/3 pi, either on top or bottom, doesn't matter to me. But then what we're going to do is just move over a pi every single time. Now, in general, when you're graphing it, you don't have to know the exact number. You can just use the same pattern that we talked about. Remember that all the asymptotes show up at half pi values. So this was negative pi over 2, this was negative 3 pi over 2, here's positive. So we know that's the distance from pi over 2. We can go that same distance from negative pi over 2, dash it in. Over here, it was at 3 pi over 2, go that same distance over. Okay, you'll notice I didn't go past that because of this restriction they gave me. I'm not going to worry about the extra asymptote that's here. Okay, but it tells us what are the equations. It literally asks for that, and on a tangent graph, I always want you to label the asymptotes. So now we're going to find the other ones. All we have to do is take the value that we just found, that was at 2/3, and we're going to add pi to get this one. We'll subtract pi to get that one. So write down plus or minus pi here, and we're doing one at a time. So 2/3 plus 1 is 1 2/3. That's 5/3. So x equals 5/3 pi. Okay. I do want you to write it as an improper fraction. Mixed numbers aren't cool attached to pi. Over here, then we're going to take 2/3 minus 3/3, so that's a negative 1/3. Again, you can label it top or bottom, does not matter to me. And then go ahead and put them on the line. It does say equation, so you got to write them out separately. All need an x equals. You could also use theta equals if you prefer. We use them interchangeably. I'm using x because that's how they denoted it in the restricted domain here and in our equation. So now that we have that, we're just going to visually eyeball the middle. But again, it's that same distance from all of these in terms of where they originally were. I was at pi, moving over to the right a little bit. Okay, if you just eyeball the middle point, it's pretty easy to see where they go. Okay, this is actually a very strange restriction. I can definitely do these ones in the middle with my shape, but as far as the extra outside here and outside here, they don't create a perfect curve if you're talking about cutting it off at those points. How this would technically look is you would have an endpoint randomly at that vertical line, negative pi over 2. Same thing over here. I know it starts low, and I know it doesn't quite get to the x-intercept, so just stop randomly before that. I'm not going to make you graph those parts. Okay, whatever your restriction is, stop at the asymptotes that are closest to it. Okay, you don't have to worry about the extra. It's strange. All right, last problem we're going to do is dealing with word problem related to what's going on here. And we can answer all of this without a calculator, really. So let's go ahead and talk about this A, B, H, and K and how it relates to the period, and let's add on the amplitude as well. Okay, so from the time before, we talked about the period and the amplitude dealing with these two numbers. Okay, you'll notice there's not a plus or minus on the inside, so we can automatically say there is not an H value. That's good news. Okay, then with these two numbers, remember the 0.8 was the amplitude, the number in front, and that, although we didn't write it out a lot, is the B value. Okay, then the A value was always the reciprocal of what you saw in there. So if you see pi over 6, the reciprocal of that is 6 over pi. Looks weird, but usually your A value has pi in it when you're talking about word problems. And the reason for that is because of the period. Remember, you're going to say 2 pi times the A value to get to the period. So our A value was 6 over pi, and you'll notice stuff cancels, coming out to a nice value. So this 12, let's just chat about it, is talking about the stuff on the inside. They use T. That's because they're talking about T in the time in hours. So this is actually 12 hours in terms of our cycle. Last thing we're talking about is the K value, which is just that 6.5 you see on the end. And it's talking about the height in meters of the tide. Okay, so here technically our B can be labeled meters, so can our K. A value, it's really just a ratio, which is labelless. I don't care if you put labels on this stuff. Okay, we do have to talk about labels for C and D to answer the question. Okay, it says, what is the minimum height of the tide during the 24-hour period? We don't have to graph this necessarily accurately to answer the question. We just have to think about what it would look like in general. So, if we're talking about cosine, we know we normally start at the maximum. Okay? Well, what's changed is our maximum's not 1 anymore. It's this 0.8. Okay? At this point, then, we take and shift it up everything, maximums and minimums, 6.5. So here's what the algebra looks like. Okay, go ahead and just do it below where you have some room. Kind of like what we had been doing, we're going to take the old max and the old min and just run it through stuff that changes it. So we just decided that our max and min are not at 1 and -1 anymore. They're at 0.8 and -0.8. And all we have to do is add that shift, 6.5, to go get our new numbers. Okay, but we also have to remember that when we're talking about these values in terms of a word problem, labels matter. So that 0.8 given in the original problem was meters. So our maximum is going to be 7.3 meters, okay, and our minimum is going to be the same thing. We have to deal with that in terms of meters, 5.7, so that we talk about our labels. Then C only wants one of them, and it wants, it looks like, the minimum value, the 5.7. Okay, now it says at what times during the 24 hours after high tide does the minimum occur? So to do this without a calculator, we just have to figure out where our period is. Okay, if there was a translation on top of this, this problem would be significantly more difficult. But because there's not a shift left and right, it's not so bad to deal with. We know that our period is 12. Okay, so the max to max is 12, which would mean our minimum happened just halfway in between that at 6. So at what times during the 24 hours after high tide does the minimum occur? Well, the first one's going to be at 6 hours. And then the second one after that, if you wanted to write another period, here's the next 12. It'd just be 6 more, or 18. And that's it. Okay, a little bit weird, but all of that one can be done without the use of a calculator. If you have questions when you're doing your homework, please be sure to come see me.